We're talking about the sieve analysis. So the sieve analysis is done on gravel and sand. We run on the whole sample, but what happens is we have sizes of sieves up until what we call number 200 sieve. Which one? This is an opening of 0.074 millimeters. Very small opening. So the smallest sieve is called number 200 sieve. It has 0.074 millimeters. One of the largest ones is half an inch sieve, which is 12.5 millimeters. So you have a very different range of sieves with different openings. When we run a sieve analysis, we run it to come up with the grain size distribution by passing it through a series of sieves and measuring the weight retained in each sieve. Where do we use them? We use them to classify soils based on many systems. One of them is what we call a unified soil classification system. The other one is called CH2 system. There are two different systems. So as I said, there are different combinations of what you are seeing here. But when you have a combination, let's say we have 10% from the silt and 90% from the sand. We have to give a name to it. We call it silty sand. Okay? And silty sand has a certain, we call it SM, right? If you have 10% clay and let's say 90% sand, we have a different type of soil. Call it SL. Well, there's no SL, I'm sorry. SC. Okay? SC. So clay sand, for example. So we're going to learn all about that later. That is called unified soil classification system. So we use this grain size distribution in here. Okay? So everything is clear about where we use grain size distribution. We use actually a lot of places, but that's one of them. All right? So now let's understand grain size distribution a little more. So these are what you're seeing here is the largest sieve that is available out there and the smallest sieve, and different sizes in inches and millimeters. So we classify soils, as I said, based on its size. We classify soils based on size. In a simple sense, in a simple manner. By the way, some of the questions I ask in class, it's usually sometimes the answer in the next page or the following page. Here's a quick thing. You know, if I'm asking a question, it's a good idea to just flip over and look at the next few pages and you'll figure out the answer sometimes. Alright? So look at the gravel size. We call them gravel, sand, silt, clay. In a very broad sense. This is just gravel, sand, silt, and clay. In a very broad sense. Relative dimensions, if you look at them here, this is kind of zoomed in. Gravel is about this size, sand is about this size. Silt, you see there's a little dot here. Okay, so compared to the size of the sand. Clay, you can't really see it at this scale. It's a very large size difference. That is why when we plot the grain size distribution curve, we plot in log scales. The horizontal axis, sieve size, is in log scales. Okay, that's why we do it, because the sizes are so large, the difference is so large. Okay, that's the reason why we do grain size distribution in log linear scale. Now, in a very simple sense, the soils are classified in different manners. There are two methods, one from MIT method, what we call, the other one is called USDA method. These are not very commonly used, but what are the most commons are AASHTO, American Association of Highway and Transportation Officials, and Unified Soil Classification System. So if the size based on AASHTO, if the size is between 76.2 and 2 millimeters, this we call it gravel. Alright? If the size is between 2 and 0.075 millimeters, we call it sand. You can draw a line here. This is where you have the number 200 sieve is. So you can't really classify into silt to clay through grain size distribution. Again, you need hydrometer analysis for this size. That's called the sieve analysis. And this side is hydrometer analysis is needed. So the USCS is almost universally accepted and adopted by the ASTM. The whole world uses USCS as far as the geotechnical engineering is concerned. AASHTO is used typically in pavement related work, pavement design, pavement analysis, pavement characterization, roads. AASHTO is for the roads, USCS is everything else. Okay? So let's go through how we calculate the grain size distribution. So we have these 5 distinct steps. They are very straightforward. One thing that I'd like to show is, let's look at the table here first. If you look at this table, the first 2 columns are nothing but the size. So the first column is the sieve size, 1.5 inch, 3/4 of an inch, and all that, or the sieve number. This size is in millimeters. The size in millimeters. So when we run a sieve analysis, we typically first take the weights of the individual sieves when they are empty, right? And then we take the weight of the sieve plus the soil after the sieve analysis. The difference between this and this, if this is A and if this is B, this MI is B minus A. Simply the difference between the sieve plus soil minus the sieve is going to give you the weight of the soil. Okay? So I didn't put that in here. It's irrelevant at the moment at this class. So when you go to the lab, you're going to actually measure these 2 columns and then do the calculations from now on. All right. So what you're seeing is the mass or weight of the soil retained in individual sieves. So what we need to do is go from here and calculate the percent passing each sieve. So what we do is first step here is we determine the mass of soil retained. Soil retained on each sieve, including the pan. The pan is what? The pan is this. If you go and look at the page 2, this is the pan. So you have number 200 sieve and we put a pan underneath, so we collect the material that passes number 200 sieve. That's actually the silt and clay. So silt and clay accumulates in the pan. Alright? So if you know the weight of the material on the pan, now you have the percentage of the silt and clay. But not separated, but just total percentage. Okay? That's the pan. So first thing is, well, by the way, before we start the sieve analysis, we know the weight of the material. Let's putting 3,000 grams, 3 kilograms of soil, right? So after running the sieve analysis test, we actually sum up the individual weights. We should get 3,000, right? If the soil didn't disappear somewhere. It never gets to 3,000. It's going to be 2,999 or something. Or it's going to be 2,998. If you get 2,500, well, you need to go back and check your calculations, or maybe you missed one sieve or something. Okay? So you need to make sure that you these matches. Actually, according to standard, if there's a certain difference that is more than a certain percentage, that you have to rerun the test. Your sieves needs to be clean and all that. These things are important. They are simple, but they are important. Now, once we have the total weight checked and calculated, we determine the cumulative mass. So if you look at this step number 2 is this right here. Step number 2, I just added them up. So summation of all these. In Excel, it's super easy. You just do sum equals sum all these cells and you're done. Okay, by the way, your homeworks will be in Excel on this one. So the step number 3 is then we determine the cumulative mass above each sieve. Cumulative mass above each sieve. That's this column right here. Let's call it 3. MC, C stands for cumulative, I stands for ith sieve, ith sieve. Okay, that's step number 3. So the way that we do this in Excel, so initially there should be the very first sieve should be no weight in it. It should start with 0. So you should have a sieve that has an opening that you know it's larger than the largest size. If you have anything retaining on that sieve, you have to rerun the sieve analysis. You have to put that larger sieve on the top, make sure that it passes. Because if you don't do that, you wouldn't know whether the size would be that size or is it maybe there's a larger size there that you missed. Okay? So very first number should be 0. Is this clear? Okay. So very first sieve 0. It needs to be larger. The size needs to be larger than the largest that you have in your soil. Now if the first is 0 retained, so the next one is essentially the summation of this plus this that goes here. Plus 576 goes here 576. So this plus this 576 plus 408, 576 plus 408 is going to give you 984. Summation of 984 plus 264 will give you 1248. So in Excel, again, usually you have to type the formula once, equals the cell above plus the cell on the left, then you are done. You just copy paste all the way down, you're done. The last number should be the same exact number as this number right here. Okay? These two. Now this is calculation, so this should be exact. The same. Because it's all calculations here. It's not a test. So if they are not the same, then there's an issue with your Excel sheet. You have to check your Excel sheet. So now let's look at the step number 4. Now we calculate your total mass passing each sieve. So it's nothing but MPI is defined as the total mass, which is here 2000 in this particular case, minus the cumulative sieve, which is essentially this column right here, MCI. So what you do is here 2000 minus 576, that's going to give you 1424. 2000 minus 984, this is going to give you 1016. Again, the same here. 2000 minus 1248 will do 752, and so on. So in here, the last number needs to be 0. So to check your calculations, every step you should check your calculations. Finally, percent passing in each sieve, or percent finer, is MPI, this column, divided by the total weight, which is 1424 in this case, divided by 2000 times 100. This gives you 71.2%. 1016 divided by 2000 times 100 will give you 50.8%, and the rest goes on like that. Now you have percent passing, and now you have the sieve size. You plot this in your x-axis and this in your y-axis to get your grain size distribution curve. Alright? What time is it exactly? My watch. 30? It's done? Oh, my watch is a little bit behind. Okay, I'll see you on Friday.